welcome to the new TCS Plus talk, which is going to be given by Claire Mathieu from ENS Paris. So before we get started with the talk, let me thank Oded Regev, who saved us from failure today because my computer was out. Let me also thank Clément Canon and India Day, Gautam Kamat, who are helping out behind the scenes. So maybe I can do a quick run through the table and we see who's here. So we have Amit joining us from University of Waterloo. Welcome, guys. Okay. Then we have Clément Canon joining us from Columbia. Welcome. Then we have Dimitris Paparas joining us from University of Wisconsin. Welcome. Grigori joining us from Indiana University. Welcome. Then there is Jiapeng joining us from UCSD. Welcome to the UCSD group. Then we have a Caltech group organized by Piyush. Welcome, guys. Then the CWI group with Shravas. Welcome. And then, my God, there's a lot of people today. And then there's Sina, who's joining us from University of Michigan. Welcome. And finally, we have a group with Yu Cheng from USC. Welcome, guys. All right. So, okay, before we start also, let me remind you, the next talk will be 2 weeks from now, given by Bo Wagner. So today, it's a pleasure to have Claire Mathieu from ENS Paris give the talk. So Claire got her PhD from Université Paris 11, I think.
Correct.
And then she was a professor at the same university, for a few years before moving to Brown. And then she was a professor at Brown, and she returned to France, I'm sorry, Claire, but maybe a couple years ago?
That's right.
Okay, well, so she's now a full professor at ENS Paris and also at CNRS. So Claire has done a lot of work in mostly around approximation algorithms, but also semi-definite programming, online learning. As I was looking up her webpage, I just realized that she's starting an online course on Coursera on approximation algorithms, which is starting next month. So anyone at the end of the talk want to learn more, I think they should take her course. It sounded exciting. And so today she's going to tell us about joint work with Vincent Cohen-Haddad and Philippe Klein, that appeared at the past Fox on approximation algorithms for k-means and k-median. So thanks a lot, Claire, for giving the talk.
Thank you. It is my pleasure to be here this evening. Let me give you a warning that the Coursera course on approximation algorithms is actually at a much lower level than what I will talk about today. Today is the 1-hour version of the talk that was given at Fox a couple of weeks ago about local search and approximation schemes for k-means and k-median in Euclidean and minor free metrics. Joint work with Vincent Cohen-Haddad and Philippe Klein. Sorry you cannot see me live, but at least you can see a picture of me, at least on the first slide. So, clustering. There's an example of it in front of you on the first slide, a bunch of points, and then they're grouped according to a proximity in space to form 3 clusters, red, green, and blue, with one center. There's another example of clustering. If you look at the 3 authors of this paper, if you look at these pictures, what you have a lot in common. Look at the hair, same style. Look at the color of the shirts, similar colors. So maybe it is not just chance that we happen to work together on clustering. Clustering, what kind of problems are we talking about here? We're talking about theoretical models for clustering, facility location, k-median, k-means, and extensions. All of them in one form or another have to do with the picture you see. You have a map, and then you have red dots. These are some centers, facilities, maybe stores that you want to open, and each store is going to serve customers who are located in the vicinity of the store. So we'll talk about two results mostly. First, local search is an algorithm that gives you a polynomial time approximation scheme for uniform facility location in planar graphs where the edges have weights, non-negative weights. Second, it's also an approximation scheme for k-median in the same setting. So there are some extensions, but these contain the main ideas. This talk will be technical, since it's...
We can't see any slides here. We just get a picture of your lovely face, but I don't know if other people can see slides.
Okay. It seems like Google has a bad day today. Maybe some of the DNS attacks from last week still persist. If you click on Claire's box at the bottom, it should be better. Let's try that. And if you still have trouble, let me know.
Yeah, I'm sorry, Claire. What happened is that some of us could not see your slides because apparently...
Oh, I'm sorry.
No, it's not. There's nothing you did. It's Google seems to be having problems. I think it's okay if we each click on your little window at the bottom. This is what I've been doing, and it's been okay for me. So hopefully it's okay for everyone. If someone has a serious problem, please interrupt. It's okay in the recording, the YouTube video, so that seems to work. So I apologize, Claire. Please continue. It looks fine now.
Not to do anything. I can just keep talking.
Yes. Yes,
Correct?
yes.
Okay.
Yes, just as you were doing before.
Okay.
Sorry.
So I'm going to talk about mostly two results. One is facility location, and the other one k-median, both in planar graphs. Today, I will focus on the technical aspects, the proofs. I want to try to communicate some of the main ideas in the proofs. But the take-home message of these two results and other results and extensions and generalizations and analogous results is that local search is a good algorithm, not just in practice, but also in theory. This paper makes a case that local search works well for problems, clustering type problems, whenever you have an instance that is well structured, for example, planar graphs. So a little bit of background. For all these problems, previously, there were constant factor approximations and some proofs of wholeness in general. Let me stop for a minute on the k-median problem. K-median, you have endpoints, you have distances, you try to locate k facilities to minimize the sum of all distances from each client to the closest facility. If you are in low dimension, for example, in the Euclidean plane, your points are points in the distances are Euclidean. You want to locate k centers so as to minimize the sum of distances from all clients to the closest open facility. This has an approximation scheme going back to 1998, based on dynamic programming. On other versions, there has been some recent progress, for example, on k-means and also on k-median. Last year, there was a result, a better constant factor approximation, 2.675, the best constant factor approximation known currently for k-median in general metric space. For we try to minimize the sum of the squares of distances in the Euclidean metric. There's a paper from this year that gives an approximation scheme. Well, not quite. It's by criteria. That is, it doesn't quite open k times 1 plus epsilon and achieves a cost of opt times 1 plus epsilon. So it's a little bit worse than optimal and uses a little bit more than k facilities. Finally, very recently, two papers at Fox, one by Frykstad, Rezapour, and Salavatipur, that prove that local search is an approximation scheme for all doubling metrics, and the paper that I'm going to talk about now for Euclidean in low dimension and minor free graphs such as planar graphs. Okay, let's get going. Uniform facility location in edge-weighted planar graphs. What you see in front of you is a planar graph. The vertices are the black. The edges have weights that I did not draw. If you look at, for example, vertex U, this client, if the bullets, then U connects to the closest center, which in this case is a distance 3 plus 1 plus 2 equals 6. And the cost of this solution is you have 6 red bullets. That is, you have 6 open facilities. 6 times the cost of opening facilities plus the sum of all distances from clients to the closest centers. That's the objective for uniform facility location. Uniform means that wherever you open your facility, it costs the same. There's a fixed facility opening cost anywhere. At this time, local search is the thing in red. What is local search? Local search means you iteratively try to improve your solution. Start with the solution in the yellow rounded rectangle. You have 6 facilities, the red facilities. What do? You try to do a small change to modify the solution. For example, you take the blue facility and you try to move it following the arrow. This gives you a new solution that resembles the previous one. It's close to it. It's almost the same, except that one facility has moved. This new solution, is it better than the previous one? If it's better, then that's your new solution. And you continue iteratively doing local changes to gradually improve your solution until you get to a local optimum. So that's local search at the basic level. What we're going to study is an extended version of local search, where instead of moving just 1 facility at a time, we move 2 facilities at a time. So we take 2 of these cases, these are possibly large number of facilities, and we try to move them. Or we try to add 1 more facility, or we try to delete the facility, saving the facility opening cost. So we try all these local changes where the set of open facilities changes, and you can look at the Hamming distance, the difference between the old set and the next set. In the example on this figure 2, there's one location that used to have a facility, now it doesn't, and another location that used not to have a facility, now it does. We're going to look at local search, where you look at solutions that are a distance not just 2, but maybe 3, or 4, or 1 over epsilon. Or actually, let's go to 1 over epsilon squared. We study local search, where a local move means you can modify your solution in 1 over epsilon squared spots. And then we'll prove that this gives us an approximation scheme.
Here?
Yes.
A small question. Are we keeping the number of facilities fixed here?
No. It's a uniform facility location. So you're allowed to add a new solution, add a new facility, sorry. Then solution that has 1 more facility, you pay in addition the cost of opening this facility, but you gain the fact that all the neighbors of this new facility now can connect to it. So it could be better. And if it's better, that's an allowed local move.
I understand. Thanks.
So you keep trying solution by adding or deleting or moving facilities, but with small square changes overall, until you find a local optimum. That's the algorithm. I claim that this is a polynomial time approximation scheme. I claim that the final solution, that is the local optimum, has value close to the value of the global optimum. Why is that? Why is it that when we have a solution that's locally optimal, its value is at most 1 plus epsilon opt? Here is the proof. So this is the start of the technical part. The output of the algorithm is a local optimum. Let's call it L. L is a set of centers, facilities, opened by our locally optimal solution. We want to show that its value is close to an optimum value. So let's look at the global optimum. Your globally optimum solution, the one that minimizes your objective overall, let's call it C, and let's color it pink or purple. Let's say pink. So we have two solutions, the black solution, the local optimum, and the pink solution, the global optimum. Let's put all these facilities on our graph. And let's focus on that set of facilities, L union C. Let's call this set F. The set F is a set of all facilities that appear either in the global solution, global optimum C, or in the local optimum L. Now that we have this, in this set of facilities F, each client, we can look at which facility is close. For example, in the yellow region in the center, the clients in there, their closest facility is the pink facility, the optimum facility from C, dead in the center. On the other hand, on the bottom right, the brown region, all the clients connect to the pink facility at the bottom. So what we have here is we have partitioned the set of clients, the set of vertices of our graph, according to the closest facility in L union C. That is, we have partitioned our graph into Voronoi cells. Here is what we're going to do. We have a construction here, bear with me for a minute. Each cell. That is, whenever your graph has an edge whose two endpoints are both in the same cell, we contract that edge. So if you focus, for example, on the yellow, what you see is this subgraph is connected. All these vertices, their closest neighbor is the pink facility in the center. It's a connected subgraph. When we contract all these edges, what do we get? The entire yellow cell collapses into a single vertex, the contraction of all these vertices, which really represents the pink facility. Do this for every cell. You get the graph on the right-hand side. This graph has one vertex for each facility of F. That is, it has, in this case, 3 pink vertices and 3 black vertices. And you have edges that denote adjacencies between the regions. Now, the original graph was planar by assumption. The new graph is still planar because contracting an edge preserves planarity. So we have a planar graph G over the set of all facilities of the local or global. We're going to work with this graph. This is going to be a major tool for analyzing the local search algorithm. What can we say about this graph? I just said this graph is planar. So how can we exploit that? What do we know about planar graphs? One of the first things I learned about planar graphs is that planar graphs have small separators. That's the famous Lipton-Tarleton theorem from the 1970s. If G is a planar graph, then there is a balanced separator partitioning a set of vertices, partitioning the graph into the left side, the right side, and the separator, such that it's balanced. Each of the two sides has at most 2/3 of the vertices. At worst, the unbalance is 1/3, 2/3, and such that the separator itself has only of order square root n vertices when you have a graph G with n vertices. Okay, so that's a well-known theorem about planar graphs. This theorem has a corollary. You can take this theorem, you can apply it again and again and again by recursively, and what do you get? You get something like this. You have a first separator that partitions your graph into two parts. You separate again, and you continue until you get to small regions with only a few vertices. And what do you prove by applying Lipton torsion recursively? That every planar graph has a partition into regions such that each region is small, a partition into small regions. Each region has at most 1/epsilon² vertices. That's the value at which I chose to stop. And if you look at the boundary vertices, the separating vertices, the vertices that enable you to connect to other regions, there's at most epsilon n total. Okay, so every planar graph has a partition into regions that are small and whose boundaries have total size that is small compared to n. So planar graph can be disconnected, separated into very small parts. How do we use this? We're going to use this because we're trying to analyze the local optimum, our solution L. I started with the global optimum, solution C. What I'm going to do is I'm going to modify C to make a new solution that is close to optimal, a near optimal solution, and that has some additional structure. And the way I do it is to take my globally optimum solution and to add to it all the boundaries of all the regions. All the vertices that are in the red parts, they can be pink, they can be black. I take them all, I add them to solution C. I get a new solution, C prime. I claim that this solution C prime, it's no longer exactly the optimal solution, but I claim that it's still close to optimal. Why is that? It's easy. There are two parts to this. The objective has two parts. One is the distance from each client to the closest open facility. Well, all we did when we went from C to C prime is we opened more facilities. So the distances for the clients can only get better. So that part is easy. The other part is the cost of opening facilities. Opening facilities, well, what did we do? We just opened a whole bunch of more facilities, a whole bunch more. We opened all the facilities in the red parts. That is, all the facilities in the boundaries of those regions. But what I just said is that this separator theorem implies that these boundaries are small. So what this means is that actually C prime has only a few additional open facilities compared to C. So C prime is near optimal.
There?
Yes.
Isn't it small compared to the union of L and C? So if L is much bigger than C,
that's correct.
Okay.
This is correct. You're right, but actually, okay, I was going to sweep this under the carpet, but actually, L, the number of facilities opened by L is because it is known that the locally optimal solution is a constant factor approximation. This was already known. Therefore, that precludes L having lots and lots and lots of facilities.
Oh, I see, great. It's more constant factor more.
Yes. So constant factor more, so that's okay. And there's a big O in what I wrote. So So you're fine. C prime is near optimal. So we actually can do the proof without using this argument, but I find that it's more intuitive to first argue that C prime is near optimal. Okay, so what we're going to do now to analyze L, the local solution, is we're going to compare it to C prime, to the enhanced, to the near optimal solution that has some structure. And here is what we do. We do it piece by piece. We do it region by region. For each region, so here I drew my region in yellow, but this is really the same as one of the 6 regions that was on the previous slide, that were on the previous slide. So I take a region. There's the part inside and the part outside. What I do is I define a mixed solution that is a mixture of the locally optimal solution and of the near optimal solution. Outside the region, I stick to L. I keep the facilities of L. Inside the region, I put the facilities of C prime. That is, I put the facilities of C that are inside the region, plus all the facilities that are on the boundary that I drew in green on this picture. So this is my mixed solution. This mixed solution, I call it M. Actually, I should really call it M of R for region R. There's one mixed solution for each region. What can we say about this mixed solution? It's not quite the locally optimal solution, but it's not that different. So let's compare L to M. Instead of comparing L to C prime, for now, we will defer that for a bit. And for now, we just compare the local solution to the mixed solution M. 2 parts to the objective. 1, facility opening cost. Facility opening cost. What happened here? We opened the same facilities outside the region. Inside the region, we opened a different set of facilities. The 1, 2, 3, 4, 5 centers of L, facilities of L that were inside have disappeared, and we've added the 5 on the boundary plus the 3 pink ones. That's 8 of them. But really, M only differs inside the region. And because the region has size at most 1 over epsilon squared, and because L is a local optimum, we deduce that the cost of L is at most the cost of M. It's less than or equal to the cost of M. Okay, so this is the first step. How do we upper bound the cost of our locally optimum solution? We can say that it's less than or equal to the cost of solution M because solution M is only different inside the region, and the region is small. And L is a local optimum. Okay, so the difficult thing, the slightly difficult thing, is to look at the difference between L and M in terms of the cost of connecting to clients. There are 2 lemmas here. One case for clients that are internal to the region, and one case for clients that are external to the region. Now here, I don't know if you noticed, but there's region and region. If you look at the regions that I constructed, each vertex was a facility. But if you look at where they came from, each vertex comes from the contraction of a bunch of clients. So really, I'm keeping both graphs inside my head. I have a graph where each vertex is a facility, but I'm also thinking of all the clients associated to that facility. So now I'm thinking of all these clients, and I'm thinking about the cost, the connection cost in L versus the connection cost in the set of facilities that I just defined in M. So I claim that if a client is internal to the region, meaning connects to a facility that is internal to the region, then the distance from X to M is at most the distance from X to the optimal solution. Proof. Let's look at the distance from X to the optimal solution. So I have two case drawings here. This client X, it's inside the yellow region. I have two cases. I have two clients X that are drawn. Both of them, I look at the pink connection that connects them to the closest op facility. Maybe the closest op facility is internal. Maybe it's outside. If it's internal, very easy. This facility is a facility of M. So the distance from X to M is exactly the distance from X to C. We have equality. Second case, imagine the facility was outside the yellow region. So what does it mean? How can client X connect to a pink facility that's outside? It must mean that X was in a Voronoi cell that was on the boundary. Therefore, it's in a cell of one of those boundary facilities that I drew in green. Therefore, what this means is that if you look at X, if you look at it, the union of L union C, it's that green facility. So the distance from X to M is exactly the distance to that green facility. And that's less than the distance from X to facility C outside. So no matter what, internal clients have a distance, a cost, a connection cost in the solution M that is at most the optimal distance, their cost in opt. Internal clients, their connection in the mixed solution, they pay at most the optimal cost. Second, clients outside the region. With a similar reasoning, you can argue that what they pay to connect in a mixed solution is at most the connection cost in L. At most, the cost to connect in the locally optimal solution, in solution M. I'm not going to go through this. It's only 2 lines. It's very easy, but let me skip that because I repeated it enough on the previous slide. It's analogous.
One
yes.
Technical comment, you might want to try using the mouse to point, if it helps. Yeah, thanks.
Here,
if
like
it helps,
can you see my mouse?
Yes. Thanks.
Very nice. So that's my pointer. Very good. The distance from Y to M is at most the distance from Y to M. Good, thank you. So now I have argued 3 things. The locally optimal solution, its cost is at most the mixed solution. For clients internal to the region, their connection cost to the mixed solution is at most what they pay in opt. For clients outside the region, their connection cost to the mixed solution is at most what they pay in L. So I wrote this in English. Then I write this in first line, cost of L is less than or equal to the cost of M. Second, so now I can use these observations to express the cost of M and the cost of L. What is the cost of L? The cost of L is the cost to open facilities of L plus the connection cost inside the region, plus the connection cost outside the region, by definition. The cost of M is the cost of opening facilities in M, plus the inside M, which by our lemma is at most the distance from X to C, plus the connection cost outside the region, which by our lemma is at most the distance from Y to L. So what we observe is when we put all this together, there are some cancellations. The sum of the outside cost disappears. It cancels. The cost of opening facilities that are outside, they cancel. And so we're left with the following inequality. The connection cost of L inside the region plus the facility opening cost of L inside the region is less than the optimal cost inside the region, optimal connection cost, plus the facility opening cost of N inside the region. Very nice. Very nice because this is all local. It's all internal to the region. And the regions form a partition of the whole graph. So we can just do this for every region and sum everything. When we sum everything, what are we going to obtain? The first term, when we sum over every region, gives us the connection cost of L. The second term, on the left-hand side, when we sum over every region, gives you the facility opening cost of L. So the entire left side is just the cost of L, the cost of a local solution. And what about the right-hand solution? The right-hand side? The right-hand side is, we sum the distances, we get the connection cost of opt. We sum all the facility opening costs, we get the opening cost of C prime, of C plus the boundaries. And so, when we sum over all regions, what we get is the cost of L is at most the cost of C, opt, plus the cost of opening all the boundary facilities, which is small compared to opt. And so that proves that local search for facility location gives you a near optimal solution. It proves what we wanted. It proves that locational time approximation scheme for uniform facility location in cradle graphs where you have some edge weights. Except, Claire, yes, you didn't, yes, except,
Well, we were confused
that this was polynomial time.
Wait, Claire, I think there's a question.
Yes.
But it, can you say it again? We didn't hear you very well.
Question on this slide?
No,
Okay.
the previous one.
Previous one, yes.
When you add all these boundary facilities,
Yes.
it seems like that the cost originally was kind of high. So how do you?
The total number of boundary facilities is at most epsilon times the number of vertices of this graph. This is a contracted graph. So it's the number of pink facilities plus the number of black, the number of facilities of opt plus the number of facilities of L. And we know that this is a big O of the number of facilities of opt.
I see. Okay, thanks.
It is also, here you can see, actually, since you had a question about this point, you can also just replace number of boundary facilities by epsilon times the cost of L plus epsilon times the cost of C. And then if you plug that in, well, you know, this is not going to change much. It will just give you minus big O of epsilon times cost of L is less than 1 plus big O of epsilon times the cost of C. That's irrelevant. So it all works out beautifully. Except for the polynomial time. So let's look at the runtime of this algorithm. We have this. In one iteration, we look at all the sets that resemble the current set, except we modify relatives. That seems to take, naively, it takes n to the 1 over epsilon squared. So that's how many repetitions do we have? At every repetition, we improve the cost of a solution. So the solution will get better and better. And when do we reach the optimal solution? Well, we don't know, because maybe the increment is small, and conceivably, depending on the edge weights, it could be, and bad choices of S prime, it could be that there's a path to a local optimum with a large number of iterations. Conceivably, you could have an exponential runtime. So to take that into account, what we analyze is not quite local search. It's a variant of local search where we only allow a move from S to S prime if S prime is significantly better than S. It must be better than S by a factor of at least 1 minus epsilon over n. Okay, so that's our new rule. Our new rule is we only allow a move from S to a neighboring S prime if S prime is better than S by a factor of at least 1 minus epsilon over n. This way, we make significant progress at every step, and that's how we can prove that the number of iterations is polynomial, and therefore this is polynomial time. So we have to plug that into the proof. We modify the proof a little bit. It adds a little bit more to the math, but it still works out to show that the solution is still near optimal in the end. So that's the actual p-test for uniform facility location in planar graphs. So what can we do with it? Do more with this. Extensions. So we've solved the basic problem. Objective. Instead of, for each client, looking at the distance to the nearest facility, let's look at the square of the distance. Well, that is fine. That's fine because we never really, let's see. One problem with the square of a distance is that it's no longer metric. It no longer satisfies the triangular inequality. However, we never used the triangular inequality. All we used is less than or equal. All we used is the distance from X to this facility is less than the distance from X to that facility because it's in a certain Voronoi cell. That was our basic argument. So the crux of our argument is just this distance is less than that distance. And that's also true when you go to squares. So the proof still works in the same way if we look at the squares of distances. What if we replace distance by some other function of a distance, something that is monotone increasing? Then it still works. So that's starting to look more general. No, the cost of connection can just be graph-induced costs, but they don't have to be exactly distances. Next extension. What if we go away from planar graphs? And instead, what if we look at minor closed graph families? Say a graph that can be embedded on a torus. Then the proof extends. Why? Where did we use the fact that we have a planar graph? We used it in two places. We said, when you have a planar graph and you contract an edge, your new graph is still planar. Well, that's true for a minor closed graph family as well. In fact, it's almost a definition. If you have a graph that belongs to a family that's minor closed, you contract an edge, you're looking at a minor, so it's still in that graph family. And then the other place where we use planarity is the Lipton tangent, and it's applied recursively. Some versions of this theorem still exist for minor closed graph families. So we can still use this extended proof to get an approximation scheme for facility allocation in minor closed graphs. Next, what if we are no longer in planar graphs, but now we are in Euclidean space? The main difficulty is the separation. The Lipton torsion theorem says if G is planar, then there's a small square root n balance separator. What is the Euclidean analog? In 2 dimensions, there's a natural analog, the isoperimetric inequality. If you have a ball of surface n, then its perimeter is big O of square root n. A ball that's like a Voronoi cell, right? So that suggests that there's also a small separator property that also holds in the Euclidean plane. And in fact, it was used, stated, and proved by Adiprolu and Harpeled in 2014. So the analog to the Lipton torsion theorem can be stated in a Euclidean space. In a Euclidean plane, in R cubed, and in R to the 4th, and in any Euclidean space of bounded dimension. Of course, the parameter is a little O of the surface, but the higher the dimension, the worse things get. Once we have that, we can adapt the theorem, the R division theorem, the partition into parts that are independent once you throw in the boundary. What you do is, you have your facilities, you have the Voronoi cells. What you do is, you can add a few points, a few facilities, so that the Voronoi cells can now be partitioned into small regions that are well separated with a small, with few boundary Voronoi cells. So perhaps the main difficulty was to try to figure out what was the right property. And once you have stated the right property, then you can use it, and the rest of the proof goes through beautifully. You can just plug it in, and local search yields a p-task for uniform facility location in Euclidean space of bounded dimension. Except again for polynomial time. What is local search in Euclidean space? You have your potential facilities, some locations in space. You try to add one facility. Where are you going to put it? If you have a planar graph, you just say try every possibility. If you're in Euclidean space, you cannot say try every possibility because that's infinite. So again, we have to use a little variant of local search where we use discretization. But this is sort of it's obvious. You can't try every point in the plane, so you just discretize. So the result extends to Euclidean space. Next, we assume that every time we open a facility, we pay a cost that is the same at every vertex. What if the cost varies on a per vertex basis? We don't know. We assume that every client can always go to the closest. A facility can be used to serve lots and lots of clients. What if you have capacities? What if a facility can only serve a bounded number of clients? Open. We don't know how to do this at this point. What if opening as many facilities as we want, but paying F for each facility we open? What if we have a hard constraint on the number of facilities? What if we're only allowed K facilities? It's the hard constraint. Then we get to the K median problem. So here the problem changes. And this is what I'd like to talk about during the second part of this presentation. What I thought of as the second half, but this really is the next 3 minutes, I guess.
I think.
Yes.
We started a little bit. Well, I don't know what you want to do afterwards, but we started a little late, so you have 10 minutes, I would say.
10 minutes. Okay.
No.
So you give me 10 minutes, then I will talk for 10 minutes.
Sure. I mean, if you, yeah.
Yeah. I'm happy doing that.
Okay.
No,
I think you have 10 minutes. Yeah, that's not a problem.
Okay. So what happens if we have a hard constraint. Then our proof fails because we're not allowed to add boundary facilities. We can't add a few more facilities. We cannot even add one more facility. In fact, when the number of facilities is a hard constraint, opt of k can be very different from opt of k plus 1. Here is an example. You have k equals 3. You can open 3 facilities. Your input consists of one cluster of points very close to one another, a second cluster, and a third cluster. And these clusters are very far from one another. Then you just open one facility in each of 3 red facilities, and your cost is, if I dare say, it's approximately 0. With the same input, if instead you're only allowed 2 facilities, then you can only open facilities in 2 of the 3 clusters. And the clients in the third cluster, they have to pay, let's say, infinity to connect to the red facilities. So it seems that we cannot add a few more facilities. Therefore, we cannot use this boundary to separate one region from the rest. Therefore, everything we did fails. That seems to be a major problem. Major, except I wrote this theorem that local search is still a p-task for k-median in edge-weighted planar graphs. So how can we prove this? We need another idea. Well, first, what do I mean by local search? Local search now means we move from a solution S to a solution S prime that resembles S. It differs in at most a small number of facilities. And in addition, it has at most k open facilities. So that's the only difference between facility location and k-median for local search. If I look at this quote hard example, it's actually not hard for local search. Local search knows how to handle this. Now, this example, one feature of this example is that, of course, having the right number of facilities is critical, but actually it's obvious what to do. You look at this and you say right away, I want to put one facility here, one there, and one there, because they're just so far apart. So you look at this and it's obvious to you, the human. Well, local, and it's obvious to local search as well. Local search knows how to detect situations like this. So this is not a counterexample to the behavior of local search. It just means that our analysis tool was insufficient, but it doesn't mean that local search is not going to work. So what is the new idea? Here's the intuition. Consider the opt solution in this drawing. You have most of the points are in this area of the slide, and then there are a few at the other end. Local search will place one facility here correctly. Opt places one facility here, and the other k-1 facilities in this group strategically positioned. What will local search do? Local search will correctly place a facility here, and then try to do as best as it can in this area. So here's, for example, what could be the local optimum. The same facility is chosen here, serving these 5 clients. And here, that is a local optimum that is different from the red solution. The black is different from the red, but then we're sort of back to something that is kind of like what we were thinking about when we are studying facility location. So the ways in which k-median is different from facility location, the ways in which the hard constraint are troublesome, is exactly the way that helps local search determine where to put facilities. And in the rest of the input, in that zone here, if you look at this, you see that the exact value of k is not really critical. If here you have 1, 2, 3, 4, 5, 6, 7, you have 10 facilities. If you only had 9, the cost would not be much worse. Between opt of k and opt of k plus 1, it's not that different here. What's critical is that there's a facility there, not that you have 10 facilities here instead of 9 or 11. So this suggests that you have some areas in your metric that are perhaps isolated from the rest. And in those areas, probably local search is going to behave approximately like the global optimum. And now we need a definition to try to make this hold. So again, the analysis works by carrying in our mind simultaneously the optimal solution C and the local solution L. Let's consider one set of points, two cells. The points that are served by F, the red bullet, in solution C. That's the pink area here. And the point that are served by L, the black bullet, in solution L. That's the cell that is gray here. And consider the common part. The common part is the part in yellow here. Let's say that this pair of facilities, one in C, one in L, is isolated if the yellow is most everything. If you look at solution L, most of the clients served by L are served by F in solution C. That is, most of the points in the gray region are yellow. The gray part is very small compared to the yellow part, the gray outside part here, the difference. And similarly for F, if you look at the clients served by F, the extra part, the pink part, is small. Most of them are in the yellow part. So you say it's isolated if when you overlay their Voronoi cell of F in C, of L in L, you look at which clients are served by them, it's almost the same set. Here's what we prove. We prove some robust property of K-median, of global opt. Let's look at the facilities of global opt that are not isolated. You have fewer than K. You have K prime. So the isolated facilities, that's special. The rest of them, K prime, this is robust. We can remove a few of them, an epsilon cube fraction, and the cost will not change by much. The cost will remain, the additional cost will be order epsilon times the cost of C or of L. So once we have this, we're in good shape, because it means that on those, so the isolated facilities, they're easy to identify. The non-isolated facilities, instead of studying C, the optimum, we can look at the version of C where it has slightly fewer facilities. We have removed epsilon cube K prime facilities, and now we have some room to play with. Now we can use the techniques we had before. We can do the partition, the boundaries, we change our parameters, then we add the boundary facilities, and then it creates some independence, and then the analysis is going to work. So we just have to do this carefully because we have the isolated facilities on the side that we cannot completely forget about. But this is the main idea. The robustness theorem does everything. So, theorem. We do a slight extension of isolation. And then we say the key lemma, the critical lemma, is the following. If you look at the facilities that are not isolated, let's call them C bar, the facilities of opt that are not isolated. We can map them to facilities that are different from themselves in such a way that if we do a reassignment if we take all the clients of those facilities, and instead of assigning a client to facility X, we assign it to facility f of x. If we do that for every x, then the additional connection cost will be not exactly small, but not too large. This is the key lemma, which you could prove by, I will skip the proof, and I will just say how to use it. How to use it is, once we have this map F, for each facility X, we draw an edge to f of x. It's a directed graph. Every vertex, non-isolated vertex, has R degree 1. Such a graph is very special. There exists a 3 coloring. Therefore, there's some color class that captures at least 1/3 of the facilities. Therefore, if we partition it into many parts, 1/epsilon³ parts, at least one of them, we can reassign all the clients, and there's only a small additional cost. And that's how we can remove some facilities. To prove a theorem, the final thing to do will be to remember what happened in the old paper by Jane and Bazirani about constant factor approximation for facility location. What did you do? There were some LPs, there was some rounding, and what did the analysis do? The analysis did some reassignment. The analysis said, there's a client that in some solution connects to a facility that really serves another client, that in some other solution connects to some other facility, that creates a path of length 3. We can follow this path, and we can use this to reassign this client to that facility at distance 3, and then we sum everything, and somehow things work out. Same idea. Same idea, what do? We have a client connected to a facility. This facility has another client that connects to a facility of the local solution. That has a client that connects to another facility of C. We use that to reroute clients to new facilities. And we lose a couple of factors along the way, but that can be done to prove the key lemma. Recap. Key lemma leads to the robustness theorem. Non-isolated facilities, we can remove a few of them, a small fraction of them, and it doesn't change opt. The robustness theorem gives us the p-task. And so we have that local search is a p-task for k-median in edge-weighted planar graphs. So these are the two results. Uniform facility location, k-median in edge-weighted planar graphs. These are the two proofs that I did. The first one fully, the second one a little bit quickly. Take-home message, local search is good for clustering type problems in instances that have some kind of additional structure that enables a partition, some kind of separation property. And this is it. Thank you.
Thanks, Claire. Sorry, the clapping is always a bit of a challenge online, but
a downer.
Huh?
It's a downer.
Yeah, well, there's a way to clap in the options somewhere, but I can never figure it out. Okay, so do we have questions? Anyone? There's, there you are.
That was not real.
It's heartfelt.
Sorry, I don't believe it.
It's heartfelt. Okay, so questions?
Question, for the first problem, is it possible to get a faster beta instead of n to the power 1 or epsilon squared, something that is polynomial and n?
Yes. So the question is it possible to get a faster p-task since the first part was this local search algorithm, n to the 1 over epsilon squared? I wish.
But regional partners that prevents that, right?
I wish. I would say this is open. I would say clearly n to the 1 over epsilon squared. You don't really want to try everything, right? You'd like to try sets of facilities that are somehow if you're going to try to change two facilities, you don't want to put one in the southwest and the other one in the northeast, because that's independent. So you would like your choices to be somehow connected to one another. So maybe you could choose a first location where you're going to change your center. And then the other locations where you're going to put or remove some facilities should be in the neighborhood of that first choice. So that first choice, you have n possibilities, but then the others should be somehow nearby. So that's as far as I got thinking along these lines. So this is open. I don't know how to get better than n to the 1 over epsilon squared.
I have another question. So do you have a sense of what are the hard instances for local search, whether planarity is really the kind of restriction that you want to be considering, or what's the sort of the smallest change you can make to the setting that you know is going to be out of reach, like local search will get stuck somewhere far from optimum?
Well, you can construct some examples. So let's say you say local search where you change 3 facilities at a time. Then you can construct solutions where each client has basically 2 possibilities. And the typical solution, either you have 1 facility per client, or you have a single facility that's going to serve, say, 4 clients. Okay, so if that's your atomic construction of a hard construction for local search of size 3, then you can put these together and put appropriate weights so that there will be 1 local opt and 1 global opt. One of them will be having 1 facility per client, and the other one will be having each facility serve as a star of clients. And so we have some, constructions, explicit constructions where there's no link, no local move to the other, and they differ by a constant factor. But I think it hasn't really given us much intuition. So I know what works. What works is to have some kind of separation, some partition with boundaries. It's the separation that is key. But I don't have an answer to the opposite question. What makes things easy is separation. What makes things hard is not sure. I'm really an algorithms person, not a low bound person.
You mentioned at the start, if there's for general case non-planar, there's hardness of approximation results for this?
Yes, it's like 1.7, I think, something like that.
Okay, thanks. If we don't have other questions, maybe I'll take us offline. If there's any other question. Actually, Oded will take us offline. So thanks everyone for watching the talk. Thanks, Claire, for giving a very clear talk. Remind you that in 2 weeks, we'll have Bo Wagner give the next TCS Plus talk. So thanks for joining us today. Now we'll go offline, but anyone who wants to, well, you can hang out for a second. We'll just take the stream offline and then, but sorry, thanks, Claire. Sorry for it.
Thank you very much.
Thank you, Claire, from Oded.